You're listening to the Knowledge Archives podcast. Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm lucky to be joined by Dr. Francis Poulin, Professor of Applied Mathematics at the University of Waterloo in Canada. His research focuses on studying fluid mechanics, especially oceanic processes and their influences on the climate. I'm very excited to explore this unique area with him today. And thank you for joining me today. I really appreciate you taking the time, and I think this will be a very good introduction to some of the more interdisciplinary concepts in mathematics, so I'm very excited for this conversation. To begin with, I know that we'll be diving into a lot of details that many people haven't heard as much about, but before we get started with all those concepts, I'd love to just hear about your story, what you're working on now, and how you got involved in this area of research.
Okay, I'm happy to do that. So just to introduce myself to you in a bit of detail, my name is Francis Poulin, or Poulin if you prefer. I'm a professor of applied mathematics at UW, University of Waterloo. I have been cross-appointed with physics in the past and also with earth science because my area of research is in physical oceanography and also in biological oceanography. So there's a lot of intersections between mathematics, physics, earth science, and biology as well. So the first question you asked me, if I recall, was how I got into my field. So it's actually because I was a student in Alberta, which is surprising because in Alberta, there are no oceans. And as a student at the U of A, I was studying, first of all, physics. Then I switched into applied mathematics. And at the time, I thought I wanted to prove theorems about equations, which describe the world, and ended up working with a professor, Professor Gordon Swatters, for 3 summers during my program, where he was studying the oceans. Because of research that he had done, I became more experienced in learning about that. And I found it very fascinating. And very soon I realized that even though the mathematics is very beautiful, the actual physics it describes was much more appealing to me, which is why I decided to spend more of my focus on figuring out what the mathematics can describe in the world, what we can learn about it, and then how to improve these models. The equations are certainly important because we need to use them in order to describe the world, but I was less interested in the beauty of the equations as I was in how the equations can describe the world around us.
Yeah, I think it's definitely an intriguing background, and as you said, there are lots of fascinating connections with this kind of math that we'll be diving into and the real world. So when I was looking into just the background of this, I'd never heard about this in high school for sure, but it was just fascinating to me to realize how for hundreds of years there were people working in this discipline. And as someone starting out to learn about it, so for me, this might be the first time I've ever heard about it, but for you, over all of your years as a student, I was wondering what were some of the largest challenges when it came to actually getting into the complicated details?
One thing that I like to say is that the research that I do involves a lot of mathematics, a lot of physics, a lot of computing, and I think lots of fun as well. And certainly as a student, I was excited about the math part of it. That's something that I always found interesting, the physics as well. And one thing I did learn is that the more mathematics one can learn, the more tools you have in your toolbox that you can use to do different things. So there are a lot of different ways of solving problems, which is one of the beauty of mathematics. And the more perspectives we have, the more we can learn about a particular problem. And since, say, the physical world, for example, is very complicated, the various ways that we can try to describe the world, maybe using Newton's laws of motion, for example, that's basically what the governing equations in fluid mechanics are based on, which, as you mentioned, have been known for almost a couple of hundred years. So we've known what the equations are for a long time, but the equations are incredibly difficult to solve. And that's why if we want to try to solve things exactly as we normally like to try to do, there's very little we can do. And I think one of the reasons why we've been able to make so much progress in studying the oceans, the atmosphere, and many other areas of science is because of the advance of computing. And one thing that I learned fairly late as a student is that computing gives us a very powerful tool that we can use to understand the world. And if we don't want to do any computing, then we're very restricted as to what we can do. But if we appreciate that computers are becoming much more powerful and they can do a lot that would take us forever to do by hand, then there are a lot of questions in science that we are able to attempt to answer, whereas without computers, it's pretty much hopeless. So
I
I guess
think
the thing that I've learned is learning different tools in mathematics, learning the importance of computing and it doesn't actually need to be very complicated in terms of the different techniques, but approaching things from a more computational standpoint, even though it feels a bit weird at first because it's making a lot of approximations, it does allow us to make a lot of headway, whereas otherwise we'd be stuck. And certainly keeping in touch with the world, most of science is based on observations. And even though myself, I don't go and observe the ocean, in part because I'm landlocked living in Waterloo, but even if I did, it's not necessarily my area of expertise. I do study theory. That's something that I really enjoy and I've had some success in. But I certainly value having contact with people who are going on cruises, who are collecting satellite data, who are sending instruments off into the ocean in order to try to measure things as best we can. And observations don't lie. So certainly knowing what people observe and what's really going on helps us to then develop models that can hopefully describe how things are today and maybe even predict how things are going to be tomorrow or the day after that.
Yeah, I think that from my perspective, I've certainly started to see how back in my early years in education, it was definitely a very do it by hand, just have that classic process of teaching mathematics. But in high school classrooms today, they recently even started to mandate that
Mm-hmm.
people start to learn about computing and even just learning about regular mathematics, like what happens with the shape of a graph when you change these variables. We've
Mm-hmm.
started to see the role that technology is playing there. So I
Mm-hmm.
definitely think that it's great to have that early foundation, and I'm excited to see that maybe the students today who now start to enter the field of fluid mechanics, what they might do with technology in the next 5 years.
Mm-hmm.
But when it comes to the status quo of how things are, so I would really appreciate you laying a foundation to what are these important processes where mathematics can be applied, but also they have a specific
Mm-hmm.
role in our climate.
Mm-hmm. Certainly. So one question that people are very interested to try to answer nowadays is the big question of climate change. And this is a hard question, I'm not going to claim that it's a question that I have been able to answer to any degree. It's very hard because there's so much going on. What's going on in the air above us? What's going on in the oceans below? And I guess if you are wanting to study climate change, it's very natural to think about the weather and how things are changing above us. But in some sense, what is going on in the oceans actually has a much bigger impact on climate change because the oceans tend to act as a big thermal sponge. So lots of heat is stored in the oceans, and that heat stays for a very long time, which is why people say that even if we were to stop emitting lots of dangerous gases currently, it wouldn't turn things around right away, in large part because of the fact that there is so much heat stored in the oceans already, it would take decades for that to stop. So this is very general, but certainly it does emphasize, I hope, the fact that the dynamics of the oceans actually have a critical role in terms of how climate is changing. Now, that's partially the motivation for me studying the oceans, even though I don't study climate change directly. You certainly need to know the dynamics of the oceans in order to understand what's going on. And the ocean is vast, and we talk about our planet being planet Earth, but in some sense, we could equally say planet water because it is two-thirds covered in water. And the kind of dynamics that goes on in the ocean is very rich. There are large gyres in most of the oceans. Many of the oceans have western boundary currents, like the Gulf Stream, off the eastern coast of the US near Florida, where these are very large currents that are important in transporting fluid properties in biology and chemistry across the oceans. And one little tidbit that people talk about is that there are palm trees in Scotland, in large part because of the fact that we have a much more temperate climate in Scotland as compared to, say, Alberta, which has a very similar latitude. And because of the Gulf Stream transporting warm waters northeast towards Europe, it creates for a very different environment. And that's why palm trees can exist in that environment. So currents in the ocean, like the Gulf Stream, are certainly abundant in the sense that they do appear across the globe. They tend to be very large. And when I say large, the diameter or the width of the Gulf Stream is maybe on the order of 100 kilometers. And because of the fact that it's so large, it carries so much water, temperature, everything within it, trying to understand the dynamics of these is very complicated. There's certainly lots of satellite observations that can show us the trajectory of the Gulf Stream, for example. And one thing that we do see is after it separates off the eastern coast of the US, it does meander and it pinches off and it forms vortices. And these vortices tend to be also quite large, maybe tens of kilometers in radius or larger. And these can exist for months or years, traveling across the ocean, transporting the fluid and the biogeochemistry it has inside it where it goes. And this can be important in terms of the ecosystems because if these eddies are warm and filled with nutrients, then if there's a fish population that encounters it, it could help nourish them where otherwise they might die. So there's a lot of very complicated features going on, but certainly jets are important in terms of transporting properties, eddies or vortices as they're sometimes called, which can be thought of like a tornado kind of, but much bigger and much slower, also help to transport the water and the fluid properties across the oceans, all of which contributes to the interesting dynamics that are going on. Those are a couple of examples that I mentioned a lot, I think, in my research, because I do think that they are very rich and they do have a big impact in the ocean and therefore have an impact on climate change.
Yeah, yeah. It's really fascinating to hear about those specifics and to continue honing in on a little bit more of the specific nature of your research. I was wondering, maybe there's one concept that you think might be easy to explain?
So I'm certainly happy to make a parallel between something that we have firsthand experience with and what's going on in the ocean. So one of the questions that myself and other people ask about currents and vortices is whether they're stable. And one example of currents becoming unstable is that they do meander and give rise to these eddies. So understanding the stability of a current is a little bit difficult and abstract, but a parallel that I can make is if you consider a bowl. If you have a bowl, any bowl you like, as long as it's roundish in some kind, if you put in a marble at the bottom of the bowl and just watch it, it's not going to do anything. It's going to sit there and not move. If you give it a little bit of a push, what's the marble going to do? Well, if you push it away from the center, you're in some sense giving it some potential energy because it's then rising above the lowest position. If you then let it go, what does it do? Well, because it has potential energy, it is going to then exchange the potential energy to give rise to kinetic energy and it's going to fall down towards the center. When it goes to the center, all the energy is being converted from potential to kinetic, where then it overshoots and then it goes back up again. So there's this interesting exchange of potential and kinetic energies. And if there weren't any sort of dissipation going on in the world, which of course there is, we'd have this marble moving up and down forever. But there is some dissipation, it does slow down, and given a minute or so, you'll find that it will be at rest. And so this is an example of what we would call a stable state, where I'm describing the marble at the bottom, because if you give it a little bit of a push, it basically comes back to that state. And it's a steady solution in the sense that if you start off with the marble at the bottom, it's not going to move. But we can also say that it's a stable solution because if you perturb it and cause it to deviate, it's going to basically come back to that state. So that's something that we could certainly do very easily in an experiment at home. If you then take your bowl and you invert it, so take it from being open on top to open on the bottom, if you put the marble at the very, very top, if there was nothing that would disturb it, it would stay there. But of course, we know that it doesn't stay there very long because of the fact that when we let it go, it's going to deviate a little bit from that position and then it's going to fall. So what happens here is, well, the position of the marble at the very top is an example of a steady solution because in the absence of any disturbances, if it were to start off exactly at the top, it would stay there. But because of the fact that there's air blowing around it, all sorts of imperfections, it does fall. Why does it fall? Well, this position, even though it is a steady solution, has a lot of potential energy. And when it starts to be disturbed, well, it's possible to exchange that potential energy into kinetic energy, and there it speeds up and it basically falls down. So it's never going to come back to the top position, unlike the other position where it was always coming back. So these are two examples of steady solutions. The marble at the bottom of the bowl is steady. The marble at the top of the bowl is unsteady. And in terms of currents, whether they're in the oceans or in the lab experiments, one thing is that we try to analyze is what are the stability of these currents. So if the Gulf Stream, if the ocean was at rest, and the Gulf Stream was flowing in a particular direction in just the right way, it might be a steady solution, even though it's moving, in the sense that it does satisfy the governing equations. But it is going very quickly. There's a lot of energy associated with that, which could be due to kinetic energy. It's always due to some kinetic energy and maybe some potential energy, depending on the density around it. But there are some disturbances which can grow to eventually give rise to vortices in the same way of a marble at the top of the bowl can fall off the bowl. So the mathematics is very similar in spirit. The details are a bit more complicated, but one thing we try to figure out is when you have these small little imperfections, how do they tend to grow in terms of what spatial structures do we observe? How quickly do they tend to grow? And typically they're on the order of, say, days or longer. And it's a complicated mathematical problem, but these are things that we can then compare with observations to see what has the Gulf Stream been doing in its history, which it has been observed very well. And looking at the vortices that are generated, we can then try to measure how large they are compared to what's predicted by the theory. So the actual dynamics of the Gulf Stream is maybe more complicated, but there is a nice parallel between that scenario, looking at the stability of ocean currents, versus looking at the stability of a marble in a bowl.
Yeah, I think that's a really fascinating analogy, and people who might have taken physics in high school, they might even be able to understand that, because I seem to remember that from studying harmonic motion. So thank you for bringing that up. Finally, the last area of questions I had for you were a little bit more philosophical, I guess, but they're dealing with the uncertainties and assumptions in this area of work. So I'll break it down into two parts. The first part being the assumptions. I know that you were talking about how we often use computational models in this discipline. And also with your analogy, you were talking about how in real life there definitely are a lot of confounding factors that throw off our precise equations a little bit. So I was wondering if you could highlight a few of the more common methods, whether it be simulations or specific apparatuses that we use to study these processes, and what some of the assumptions are that we're making in these models of the ocean.
Okay, so I guess one thing I should say is that every model, whether it's of the ocean or of marbles or something else, is always wrong. Wrong in the sense that it can't possibly describe all the details of the world. If you even wanted to try to describe the dynamics of a marble in a bowl, well, how much do you need to include in order to describe that? And if you wanted to include every atom in existence to understand the dynamics of that marble, we don't have the computing power to do that. And quite frankly, I don't suppose we ever will. But at the same time, do we need to consider everything going on around it in order to understand the dynamics of a marble? And the answer is no, luckily for us. And every model that we put together tries to capture the essence of the problem that we want to describe that are needed in order to answer the questions we're asking. We always start off with particular questions. And with those questions, we need to figure out what's the right model or what's a simple model that we can use that captures the essence that allows us to make some deductions to then compare the results back with observations. I always believe starting with the simplest model is always the best because then we can try to validate whether the results compare with what's observed. And the results are always going to be wrong in the sense that there's always going to be some kind of error. But is the error because of how we're solving it? Or is the error because of the assumptions we're making in trying to describe it? And usually there's a little bit of both. But after we have a start, we can then figure out, well, for example, with the marble, do you need to consider the damping due to the air around it? And that's something you could then include if you wanted to have a more complicated model. And I think this is something that we strive to do. We start off with simple models that describe some aspect of the world. We solve the equations. We can compare that with the world. Hopefully, we get some agreement. If we get none, then the model is useless. We throw it away. If the model has some merit, well, what other factors can we include that we think are the next terms that should be considered in order to get more detailed answers? And this is something which doesn't really stop because there's always more physics we can include. There's always different questions we're trying to ask, but every model has to have some merit in terms of being able to predict some aspect of the world around us to some degree of accuracy. Otherwise, we shouldn't be talking about it. And how well it's going to do depends in part with how well do we understand the world, how well can we describe the world in the language of mathematics, and how well can we solve these equations using computers. And then we have to sort of infer from these solutions what kind of predictions we might be able to have. So I don't want to be discouraging because there are a lot of sources for error, but at the same time, we can describe some amazing things like the motion of baseballs, the motion of the Gulf Stream, with a lot of degrees of accuracy because we have learned a lot throughout the years.
Yeah. And then the second part of my question is finally, if people are curious to get more involved in this field, what are some of the largest open questions, the research gaps that are still being explored, and where might people get started by learning about the basics of the field and then working their way up?
So learning, I guess, for the area of research that I work in, everything is really described in the language of calculus. So calculus is something that many high school students, I think, can take in grade 12. I took it in grade 12. Calculus is beautiful. It's very rich. It's beautiful in terms of the mathematics, but it's also rich in the sense that it does allow us to describe different aspects of the world. And mathematical modeling, which is something that I certainly enjoy a great deal, starts with calculus because you want to describe the rate of change of things, whether it's the motion of a baseball or it's the motion of a current of some kind. learning calculus allows us to not only be able to do certain calculations, but gives us tools by which we can try to describe the world using things like Newton's second law, using conservation laws, and also learning physics is certainly useful because the more you know about the world, the more you can try to describe. So I would encourage everyone to be curious, try to encourage that curiosity, ask questions, look into things, and whenever you might start to answer one question, you'll find that there's many more where that came from. So I think we all have a natural curiosity about us, which I think is great to encourage. Talking to other people with similar interests can give us new ideas that we might not have had before. So there's certainly no shortage of things to do, just a shortage of times to do them.
And I think that's a very valuable perspective to end off on, especially for people who are younger and haven't had the experiences of thinking about limited time or thinking about the value that is going to come from all of these years of education because we haven't had that chance to work. So I really appreciate you taking the time to walk us through the basics.
My pleasure. Thank you very much for contacting me. I'm always happy to discuss my research and to talk to young students and share the beauty of mathematics. So thank you for asking.